Good morning and good afternoon and good evening. Thank you for joining our webinar today, and we are happy to have you with us. And today, Staffan Johansson will present you the key features, performance, and benefits, and the potential application of our newly launched FTR-210R GNSS-disciplined Rubidium Frequency and Time Reference. During this session, you are encouraged to ask us questions in Q&A chat, and we will answer your questions after the main presentation. So the webinar is recorded. We will share the recording with you after the session. Plus, we will also share the PowerPoint presentation Staffan is going to show you today, also together with the link. So I think that's all from my side. Enjoy the webinar, and Staffan, the floor is yours.
Thank you very much, Eva. And welcome everybody to this webinar about our new frequency and time reference from Pendulum Instruments. A little word about the company, because some of you may not know us so very well. We have over 60 years experience in the test and measurement business. We have our roots in Philips Test and Measurement. We were a spin-off in 1998, and the new company name Pendulum Instruments. So today, Pendulum is a global company with offices in Sweden, Poland, China, United States, and we are represented in some 100 countries all around the world. And I, Staffan Johansson, is the Strategic Product Manager of Pendulum Instruments. I personally don't have 60 plus years of experience, just 43 years and still counting in this time and frequency test and measurement business. We have a very, we don't not only sell and produce and develop frequency and time references. We have a portfolio with 5 product categories. We have also time and frequency counter analyzers, including the multi-channel, world's first multi-channel benchtop frequency analyzer, CNT104S. We have frequency distribution amplifiers, and we have 2 product lines based on acquisitions about 4 years ago. The high voltage linear amplifiers from Swedish company FLC Electronics, and the EMC scanners from Swedish company Detectors, a very well-known brand name in the EMC pre-compliance world. But now let's go back to the topic of today, the FTR-210R frequency and time reference. It's a frequency reference, it's a time reference. It has, as a frequency reference, it is a Rubidium clock that is providing the frequency stability and is disciplined by a multi-GNSS receiver, which means that we have an excellent long-term stability coming from the satellites and an excellent short-term stability coming from the Rubidium. Stability is better than 1 × 10⁻12 in 24 hours. We have a standard 510 MHz and 15 MHz sine wave output. And in addition to that, on the rear side, you can mount 4 additional outputs, either 10 MHz sine or a multi-frequency output, 0.1, 15, or 10 and 10 MHz. And on top of that, there is also an optional 0.5 Hz to 100 MHz pulse generator output. As a time reference, that means providing a 1 PPS that is more or less synchronous with the Global Universal Coordinated Time, UTC. We have 1 standard output on the front, and on the rear we have 4 extra optional 1 PPS outputs. The uncertainty to UTC is better than 10 nanosecond RMS, which is a very good value, and the whole overdrift in if you lose GNSS contact, it's better than 1 microsecond over a full day, over 24 hours. So these are the frequency reference and the time reference bullets. So there are other important bullets to mention, and most of all the optional traceability to UTC, because this is a unit where you can get true traceability to UTC thanks to a built-in independent phase calibrator that makes continuous and gap-free comparison of the received 1 PPS signals from the satellite and the internal Rubidium oscillator output. All raw data is made available to the user, and it can also generate a calibration report with data and stated uncertainties. Another important feature of this unit is it has an optional frequency measurement input to 400 MHz, which converts the frequency standard to a one-box frequency calibrator. That means you have both the timer counter needed for calibration and the reference frequency reference inside both boxes. Inside one box, I mean, of course. Other features, we have remote control and monitoring via wireless LAN or LAN. We have remote alarm messaging. We have a secondary disciplining input, not just the GNSS antenna, is an external 1 PPS sync input. And something that is new for frequency references in this category is performance upgrade via software licenses, which means that you can purchase a basic unit and then upgrade afterwards by purchasing a software license. We talk more later about all these features. A quick look at the panel. We have the main screen in the middle. We have the inputs and outputs to the left, where we on the front has a 1 PPS and 1 5 MHz sign reference output, plus 2 10 MHz reference outputs. On the rear side, we have another 3 standard 10 MHz outputs, plus the 4 optional outputs I mentioned earlier. To the left, we have 2 USB ports that can be used for various matters. You can use it to connect the mouse to use a mouse pointer on the main screen to do the settings. You can use it for calibration data backup if you plug in a memory stick. You can use it for software license update, for firmware update. You can plug in a Wi-Fi dongle, and then you have the wireless LAN connection. Traceability is an option which is software enabled via a license. And that is a very important property of this unit. Traceability in measurements per definition is achieved through an unbroken chain of comparisons to national or international standards, all having documented data and stated uncertainties. And we achieve that via this continuous phase comparison to the satellite UTC of the GPS system. Because we have a separate and independent comparator that compares the 1 PPS from the GNSS with the 1 PPS output from our Rubidium. Store that calculates parameters like average time of set, average frequency of set, etc., and produces a calibration protocol with the data. We store the timestamps in every 30 seconds in RAM, and we store the calibration results over 24 hours, once a day at midnight in a flash memory. And we have the built-in calibration report generator. And that is something that distinguishes the FTR-210R from other typical frequency and time references. They do not provide this data and calibration information. They do not calculate uncertainty, which is essential to be able to claim traceability of your device output to NIST. Because once you have traceability to the GNSS systems, you then automatically have traceability to UTC via NIST through the GPS data archive that is updated by NIST every 24 hours. I'm so sorry. And you have the traceability from NIST to UTC via the Circular T document produced by BIPM in Paris. My God. Every month. So a traditional GPSTO has no documented data, no uncertain calculation, and thus no traceability. What the heck is going on? We can produce a traceability report, and this is a draft version of it, and it will contain the day-by-day phase offset, average phase offset data to UTC with uncertainty, also the peak-to-peak variations of the 1 PPS during the day, the average 10 megahertz frequency offset to UTC with uncertainty, comments if you're outside specs or if you have too few data points during the day to make a reasonable uncertainty calculation, or if there is no data at all. The next feature worth mentioning is the frequency measurement input. That's a hardware option. You need to order that from the beginning. It cannot be software upgraded. You have a measurement input up to 400 megahertz where you can measure frequency period, pulse width, rise time, fall time, slew rate, and voltage of the attached signal, as well as time interval error. And you can also use that input for event time tagging, which is performed as a time interval between the applied signal to the internal 1 PPS signal. Performance of this measurement input is very high. First of all, you get the results both numerically and graphically, as we see on the right side. On top, you have a numeric representation of the input signal, and then in the middle you have the distribution of the values of the input signal, and on the bottom you see the time view, the time, the value versus time trend, you can also call it. And you can apply acceptance limits, as we see in the middle and the lower graph, where you set your acceptance limit for your device under test, and then you get a clear indication if you're inside or maybe outside your acceptance limits. And if you need to do any adjustment, if so, in which direction. And the basic performance is indeed very high. We have 14 picoseconds time resolution. We have 10 nanoseconds RMS time accuracy to UTC. In a second, we have frequency resolution of 12 to 13 digits. Accuracy, that is depending on the gate time. The longer gate time, the more accurate is the measurement. Over 24 hours, we have 12 digits, but already at 10 seconds, we could have at least 11 digits of accuracy. Measurement speed, if you want to do analysis of some transient or some modulated signals or whatever, you can capture the input signal up to 1 million times per second. The remote control of this unit is very flexible. You can connect to your local area network or to Ethernet in two ways, either via the Wi-Fi dongle on the front USB port or via a wired Ethernet connection on the rear. When you use it manual on the screen, the basic operation is done with your finger, it's touch screen, or you can, as I said earlier, connect the mouse to one of the USB ports and then use the mouse pointer. The remote web server function makes it possible to duplicate exactly what you see on screen, including all controls, and to operate from any remote location in the world, and also save data and save status, transfer data to your PC location wherever you are, either near the unit or far away from the unit. The main screen, when the traceability option is installed, will look like this: date and time message that is updated every second. You have frequency offset for the last hour and frequency offset for the last 24 hours, updated regularly. You have the phase offset, that means the offset of the built-in 1 PPS receiver to the 1 PPS output on the front. That is also regularly updated. And at the bottom, you have some information coming from the GNSS receiver, like your position. If you have a position fix, yes or no, and how many satellites that are used currently for the disciplining. Then you can also use the graphical screens of the same data to show the phase offset to UTC of GPS over time. This is a recording that is almost 3 days long. And you see that it's very flat. The mean value here is 3.3 nanosecond, which means that our outputted 1 PPS is on average 3 nanoseconds away from the 1 PPS from the GNSS receiver. And this is data that we provide to the user, and That is something that other references do not provide to the user. And this phase offset is the basic measurement we do, because from that we can calculate also the frequency offset. This is an example of the satellite view screen. So you see the number of satellites here with the code that reveals the satellite system and the number of that specific satellite in that system, together with position information. You get some extra information here, for example, that we are using 23 satellites of 38 visible for the moment. So the applications, as we see it for this box, is metrology in a very broad sense, from highest end national labs via military cal labs, accredited labs, third-party calibration services, and cal labs in electronic industries. All of these labs will have a demand for traceability, and with the traceability built in, they do not need to find another solution for traceability, like external comparison with other units, for example. We have industrial customers needing a house reference for R&D and test systems, especially in the telecom, manufacturing industry, aerospace and defense, prime and subcontractors who have a need for very high frequency and also time precision, and also in the civilian radar and communication equipment manufacturers. Military synchronization testing and broadcast and communication infrastructure, where you would have a need to verify sync nodes, where we can provide extremely accurate 1 PPS as a reference. So we have been talking about features. Now let's focus a little bit more on the benefits for the user. The built-in traceability, what does it mean for the user? It means secure and safe operation, because you get 100% confidence that the unit is working correctly. If it should fail for some reason, you will get an immediate notification if frequency offset is out of specs. And you have the traceability data available, saved every 30 seconds for the user to analyze. So security and safety is what you get. Cost saving is there because if you need to have a traceable reference, you can have it in mainly 3 different ways. You can have it built in, as in FTR-210R. Then you have no yearly calibration cost and no downtime. If you send it to an accredited lab for calibration, there is a fee that could be quite high, and there's definitely downtime, maybe up to a month, maybe longer. And the third alternative for traceability is that you purchase a service from your national metrology lab, which means that you have some extra equipment side by side with your local frequency reference that contains its own reference, contains a comparator to the local reference, and sends the comparison data via internet regularly to the national lab, where the data is processed, and in return the user gets a calibration protocol that is makes it traceable to the national lab. That service is normally very expensive. For example, FMAS provided by NIST, which gives, of course, also 100% perfect traceability of a time and frequency reference. It has a cost of over $8,000 per year. And you get a calibration certificate on demand whenever you like on your internal reference, all with the required data and required uncertainty. The benefit of the measurement input is that you convert the frequency reference to a frequency analyzer, a one-box analyzer. And let's have a look at the graph on the bottom. The general calibration process, that is a comparison between a reference, a known quantity, and a device under test with an unknown quantity. The result of that comparison is the data plus stated uncertainty. The reference used should be traceable to an international or at least a national standard. That is the general calibration process for any type of the parameter that you want to calibrate. Specifically for frequency, you have your frequency reference and you have your device under test, providing two input frequencies to a timer counter that are comparing these two inputs, normally phase comparison, and then you provide output data and you post-process it to get the frequency difference of the device under test to the reference. That requires two boxes, frequency reference and a timer counter. When you use the measurement input in the FTR-210R, you have everything in one place. You have one box containing both the reference and the timer counter. All you need is a GNSS antenna. So you connect the device under test and you get your traceable frequency difference to the reference. And there is no manual offline calculations to provide these, the data and the uncertainty is done automatically inside the box. So you save a bit of time there. So there's an obvious cost saving. You don't need any extra timer counter to do this calibration. And you also get a very, not to say ultra high performance of this one box calibration, because you have a very high time resolution and accuracy, very high frequency resolution and accuracy. You can reduce calibration time, you can save money. That's already the benefits. Using GNSS instead of GPS, as is commonly found in legacy frequency standards, even if GNSS receivers are nowadays the most used in frequency, in new frequency standards, but there are still very many legacy frequency standards around that use GPS only. Basically, you have 4 times more satellites in view because you have 4 times the number of satellite constellations, not just GPS, but also the Galileo, European, Beidou, the Chinese, and GLONASS, the Russian. It means you have more opportunities to lock to the satellites. You will eliminate the periods where you don't have any lock and you enter whole over. And also in urban canyons, you can be quite confident that you will have enough satellites to lock, even if you are on the ground floor in, let's say, central Tokyo or another city with very big skyscrapers around you. And benefit number 4, we have a very accurate and stable 1 PPS output. The optional extra 4 1 PPS outputs has been trimmed to have a minimal skew between the outputs that are down to a few picoseconds, to be used for time reference to multiple units where you want to have exactly the same time relationship for all these units, up to 4 units. We have an accuracy to UTC that is less than 10 nanoseconds, which is better than the typical standard, which is normally specified to be between 20 or 30 nanosecond RMS. And when you lose GNSS lock, you enter holdover with a drift that is better than 1 microsecond for 24 hours. That means 2 times better than a Stratum 1 PRS clock.
So perhaps let's finish for now. Of course, you can contact us and ask questions via email or yes. So then we will get back to you with the answers. So for now, I think this is the end. We are very happy to have you with us today. Thank you for joining webinar and being a part of this session today. And Stefan, thank you for your excellent presentation.
Thank you, Eva, and thank everyone for attending.
Okay, so once again, thank you. Have a good day or good evening, yeah, and stay tuned. Follow us on our LinkedIn account to be updated on our new products and events which we arrange. So once again, thank you. Bye.
Okay, thank you very much.